Let's look at a couple more molecules here. In fact, here's one that maybe you can try. So water, H2O, has atoms that look something like this. So there's an H. There's an H. Remember, they're in group 1, so they've got 1 valence electron. The oxygen is in group 6, so it's got 6 valence electrons. And maybe you can pause the video and bring these atoms together and see if you can't draw the Lewis structure. I'll pause, and then we'll go over it together. Okay, so we just bring them together. So the hydrogen, we move in close to the oxygen, and you can see that, let's see, that hydrogen now is pretty happy, and the hydrogen on the right-hand side is pretty happy. So that electron and that electron is now paired up here. That's making the bond, and this one is paired up, so that's making the bond. And we can write that with a line, right? So we can write the line as the shared pairs of electrons. And if you remember, do you remember the language? What do we call that shared pair of electrons? Yeah, we call it a bonding pair. And okay, so what do we call that pair of electrons that's not being shared, that's not bonding? That is called the non-bonding pair or the lone pair. So water, actually, it looks like all those atoms should be in a straight line. We'll see in the end of this chapter that water actually is not straight like I've drawn it on the page here. And it turns out these electron pairs here, these lone pairs, are going to kind of repel the other bonds around, and they're going to take a very different shape. So far it looks pretty easy. We just kind of click them together, but we've got a few molecules that are a little bit harder. So if we look at oxygen, oxygen's a diatomic. It's in group 6, that's right. So we've got 1, 2, 3, 4, 5, 6 electrons around it. So 1, 2, 3, 4, 5, 6 electrons around it. So now we've got to bring them together to share. And the idea is that they want to end up with 8 electrons around each atom to have that octet. And there's a couple of ways to do this. So we can share either one electron from each side, or we can share 2 electrons from each side. And what we're going to find is that right now we've got 1, 2, 3, 4, 5, 6. So how many more electrons does it need to be happy to have an octet? That's right, it needs 2 more to have 8. So we're going to share this electron and this electron. So we're going to end up with something that looks like a pretty weird kind of punctuation symbol. So there's my left-hand oxygen, and there's my right-hand oxygen. And I'm going to have 2 electrons from each atom being shared, and the other atom's kicking in 2 electrons. So we now have a total of 4 electrons in between there. Now, if you look at this and you say, well, that's looking kind of weird, everything actually looks pretty darn good. So oxygen has an electron configuration of 2, 6. And at this point here, now it's gained 2 electrons. So now it looks like it's got an electron configuration of 2-8, which is isoelectronic with a noble gas neon. We can also look at this more simply and just say, well, everything apart from hydrogen and helium needs 8 electrons to fill the outer shell. So the octet rule is totally hunky-dory there. And if we look at the other oxygen, we're going to see it's got 8 electrons around it. So it's also going to be isoelectronic with neon. So that full outer shell is when we've got 8 electrons around almost everything apart from hydrogen and helium that only needs 2. And we can write this Lewis structure by remembering that anytime you've got a pair of electrons, it is a bond. So when you've got 2 pairs of electrons being shared, then you've got 2 bonds. And the lingo here is a double bond, or more properly, a double covalent bond. And we still have our lone pair, so we've got 1, 2, 3, 4 lone pairs here. But the 4 bonding electrons, the 2 pairs of bonding electrons, go to forming a double covalent bond. So you might guess that 2 bonds is stronger than 1 and 3 bonds is stronger than 2, and in fact you'd be right. So in general, the double bonds are stronger than single bonds. And if I just draw sort of a fragment of molecules here, so let's say we've got 2 carbon atoms that are coming together. If they have a single bond, then the single bond, I'll go ahead and write that in blue, so that's a single covalent bond, so I'll just write single in there. It's pretty weak. And if you compare that to, say, 2 carbons with a double bond, the double bond is much stronger. Oh, if I can spell double. And then you can have actually up to 3 pairs of electrons shared between the atoms, and we call that a triple bond. And the triple bond is the strongest bond, so I'll write that in red underneath. So this is strong, or strongest, maybe I should say. And this one over here is the weakest. Okay, what we also find, so I guess going from left to right, then the bonds are getting stronger. But what we also find is that the stronger the bonds are, the closer the atoms are held together. So the shorter the bond is, and the weaker the atoms are held together in a double bond and then a single bond, the longer the bond is. So the less tightly held they are, the longer they are. And so what we find is that the bond length changes in one direction and the bond strength changes in the opposing direction. And what's really kind of neat actually is that these things vibrate. And what's interesting is that the long, weak bonds vibrate with a very low frequency. And as we go to the shorter double bonds, the frequency gets higher. And as we go to the very short bonds, the frequency gets extremely high. So here's a little animation of a guy vibrating here. That's kind of weird, right? But basically, the triple bond would be something like this. And so you are vibrating extremely rapidly. And oh, that's kind of too much to watch, isn't it? Let's go ahead and pause that video. So you can actually identify molecules based on this. So you can shine light through molecules, and their vibrational frequency actually tells you what kind of molecule you have. So we can certainly identify things out in space. We can match up the vibrational frequencies we see with the molecules themselves, so we can actually identify what's out there in space. We can also shine light through your wrist into your bloodstream, and by watching the vibration of the molecules, we can tell, say, how much glucose is in your blood. So it gives you a very nice diagnostic way to tell what's in your blood without drawing a blood sample.